Hey everyone, okay, so this is the third and final video on harmonic motion. We're going to do some of the practice problems, some extra problems for this topic. So if you want, you could pause the video right now and try doing the question yourself. And we'll go over it in a second. Now, one thing to note is that sometimes a problem may be set up so it seems like it would be much more complicated than it actually is. And it turns out that it actually will end up having a very nice, simple solution. And this is a perfect example of that. So in the first part where they want to know the effective spring constant of all four springs, it's really straightforward. We actually just consider it as if there really was just one spring. So we do what we would normally do if this was a single spring setup. Set the spring force equal to the weight of the object. Isolate the spring constant and plug in the numbers that we know, and we get our spring constant of 130 newtons per meter. So easy peasy. The only reason why we would ever have to worry about the fact that there's four springs is if they want to know information about the individual springs. So we could use this and figure that out. Or if they did the opposite, where they told us information about the individual springs, and then they want us to use that to figure out the effective spring constant. All right, now part B is a little bit extra. So the first thing to note is that they make the comment of inelastic collision. Now the moment you see that, your mind should immediately go to conservation momentum. So we say that the initial momentum of this clay is equal to the final momentum of the clay table system. So that's what I have here. The initial momentum equal to final momentum. Moving things around, we find that the final speed that this clay ends up moving at is given by this relationship. Now that we have that, we can then do conservation of energy to figure out where its max displacement is. So if you remember, whenever we do conservation of momentum, we need 2 points. So the 2 points we're going to do is the original position and the max displacement, the amplitude. Now we know the energy at the amplitude is just the straight up max potential energy. Now the energy at this point, because of the fact that even though it's the original equilibrium position, it's going to end up falling down a bit because of the added weight to a new position. So this actually is a displaced position now. And then we have a speed. So it's going to have some potential energy stored in the spring and a kinetic energy coming from the movement of the table. So our equation is going to end up being this. So our maximum potential equal to the max kinetic, I shouldn't say max kinetic, but the kinetic energy of the system plus the amount of potential between the new equilibrium and the original equilibrium points. So that's what this is referring to. Now we move things around and solve for the amplitude and we get this equation. Now I need to know what the speed is of the table clay system. So I'm going to take the equation I got from the momentum part and plug it in for V over here. It's going to drop this is going to drop one of these masses, and I'm going to end up getting this as my simplified equation. So this is now in terms of everything that I know. So taking that and plugging in the numbers I was given, I end up finding that the max amplitude is about 9.6 centimeters. And that's 9.6 centimeters from the original position. All right, now we'll work on this question. So again, you could pause the video, work on this yourself, and we'll go over it in a second. All right, now with this one, realistically, all we have to do, so the first, it's always really nice when they give us the answer. I always like that. I always like to know where I'm going to go, because one thing to note is that we can use this to kind of get an idea of the method that we're supposed to be doing. So if I look at this equation and this period equation that they give me here, realistically, this is just 2 pi rad m over k. So the main thing is that they just want me to show that if I plug in a relationship of these individual spring constants in for the total spring constant, I'll end up getting these relations, these equations that they want me to get. So the first step is just to show what the effective spring constant is as a function of K1 and K2. So this is just, you can go back in the notes in the previous video to see how I did this. I think it was in the first video. So I'll go through this really quickly, but we find out that when the force is applied, you end up getting the sum of the x values, and the spring forces are all going to be the same. So what this tells me is that the inverse of the total spring constant is equal to the inverse sum of the individual spring constants. Well, the good thing is that this rad m over k really is just m times 1 over k. So I could just take this and plug it in for 1 over k in the original period equation and end up getting this. See? Easy peasy. Next one's even easier, because with this one, they're connected in parallel. Even though it doesn't seem like it's connected in parallel, it actually still works the same way. So the effective spring constant is going to be the combination of the springs. So same thing that we saw before in the parallel setup. So once again, I take the original equation and I just plug in the sum of the spring constants. And that's pretty much it. All right. Now, I just wanted to go back. If you didn't recognize that this was parallel, one nice thing is that if you look at the forces, it will make a lot more sense. So for example, if we take this block and let's say we displace it over to here, well, this spring is being stretched, so it's going to be pulling this block to the right. But this spring is being compressed, so it's not going to want to pull it towards it, it's going to want to push it away, which is to the right. So both of these, when this gets moved, will actually push it in the same direction at all times. That's why we can kind of get away with treating this as if both springs were on the same side. All right, so this is a practice with kind of seeing how you would use the whole dampening function. So here is a pendulum, and we want to know what is the dampening factor if it loses half its amplitude in 300 seconds. And then we want to figure out essentially the percent error of the frequency. So how much does the frequency actually differ after these 5 minutes? So you can pause the video and work on this yourself. We'll go over it in a second. All right, so we haven't really gone over many of these questions, which is fine. You don't have to worry too much about it. But if you recall, we did have this equation from before. Now, I'm pretty sure I have given this equation for a spring, but as I mentioned before, it really doesn't matter. All the equations can kind of be interchanged with each other. All we'd have to do is make sure we have the right variable terms. So instead of x, we're going to use theta. And I think when we use the equation for omega, we'd have to also make sure that it makes sense for both a pendulum and a dampening scenario. So what we're going to say is, since it's going to half its amplitude, we just put in half the amplitude here and here. This is not actually doing anything for the amplitude. This is the part that's actually affecting the amplitude. This is just giving it the oscillation factor. this is the decay factor. So I'm ignoring the cosine omega t part, and I'm going to plug 300 seconds in for the time, and I'm just going to end up solving for gamma. The a's drop out, take the ln of both sides, and we end up getting that the gamma factor is this, 2.3 times 10 to the negative 3 per, hertz, if you will. All right. Now for the next part, we have to be a little bit more careful. So we have to kind of think back to the fact that we're using this form. And the equation that we're going to end up having for the dampening setup is going to look something like this. Now, if you don't see why it's like this, I'm pretty sure it was given in one of the notes. But again, I think it was meant more for the spring. So what we have to do is just replace the m over k with g over l. We could pull out that g over l so that we can kind of get this term. You'll see why we're going to do that in a second. Now from here, in order to get the frequency, we just divide it by 2 pi. So we have to include this 2 pi term in there. And then we just use this function that they tell me. So the original frequency was 1 over 2 pi rad g over l minus the new one, which is this entire term, over the original frequency. So this 1 over 2 pi rad g over l and this one are going to drop out. So what we end up getting is this. This big bracket here is what I actually want to focus on. So we need to analyze what is 1 minus rad 1 minus L gamma squared over G. All right. Now we could plug it in, but we can be a little bit nicer with this. Here it is. Okay, so what we have to do is we have to do what's called the small x approximation. So what that means is that when we have a radical function like this, and this is actually why we want to rewrite this original frequency in this weird way, even though it made it look a lot grosser, we can simplify this radical 1 minus junk term by using the small angle approximation, saying that if this number is really small, which it is, 2 times 10 to the negative 3 squared divided by 10, what we can say is that it's related to 1 minus x over 2. We can ignore all these higher order terms because, again, this number is going to be so small that when we square it, it's going to become significantly even smaller because that makes this gamma to the 4th power divided by g squared. So yeah, we're just going to replace it with 1 minus x over 2, where x is this entire term. So again, in this bracket, we end up getting 1 minus, and then over here we get 1 minus x over 2. Well, those two, the 1 minus 1 drops out, so we end up getting this, x over 2, which is what this is saying here. This is the x term, and this is over 2. So I can take the number that I got before, plug it in, and end up getting this. All right. And that should have been it. So you could use that as a jumping off point to see some of the other problems. Again, work through some of the questions in the textbook. If you have any questions, please let me know. Otherwise, I'll see you next time. See you later.